by right? This is our x of t.
Mm-hmm.
All right. So what we did in recitation this week, for those of you that were there Monday, and those of you who will be there today, was we did individual integrals for every harmonic, right? So last time, I think you saw, tell me if this is wrong, because Dr. Obaid, he doesn't know what Dr. Obaid gave me today's lecture. Pretty much non-existent. Most of that writing is my own. But anyway, for A1, it was 2 over pi e to the minus j over 2. Is this right? We guys have that in the notes?
Okay.
Okay.
No, 1 over. The first one, 1 over pi.
Is 1 over pi? Okay, and what do you have for A2 then? That one would be wrong. What was it?
1 over 2 pi.
E to the positive j pi over 2? Okay. So you were just doing each of those integrals individually, and those are the answers you get, right? So what we want to do, though, is rather than just look at each individual harmonic, right? Like if we want to reconstruct a wave, any signal out of a cosine, we need to look at, generally speaking, an infinite number of harmonics, right? So it makes more sense rather than solving this one piece. Okay, for any given harmonic, we now want to solve it for what we call a sub n. And what we'll write in here now, for any harmonic, j omega n. And just to make this a little bit, to clarify this, because sometimes omega can be confusing if we're talking about omega of the signal or omega of the cosine. So let's just write this as 1 over t, integral across t, x t e to the minus j 2 pi over t. Okay. Where capital T is the period.
So you said there's 2 omegas then?
Well, you can talk about the frequency of the original signal, and then you can talk about the frequency of the cosine that you're checking, like whether or not that cosine is in that signal. Okay? There's like a x of t is like, in this case, sawtooth. There's a frequency associated with that, right? This e to the minus j omega nt is this. This piece corresponds to the cosine that you're checking to see if that's in that signal. Okay? But I just want to sort of, I like having it in the form of period because the period of the original signal never changes. Okay? You don't want to have too many omegas floating around. I think it's a little bit more clear cut. Okay? So in this case, let's go back to our original problem and let's solve this. Okay. So what do we have here? What's our period again?
2 pi.
2 pi. So this is equal to 1 over 2 pi. What am I going to integrate from?
Minus pi to pi.
Minus pi to pi. Okay, what's x of t?
1 over pi.
1 over pi.
1 over pi.
T over pi. Okay, and the way I got that is I'm looking for what is the equation of this line between negative pi and positive pi. Okay, so this is a big deal. Dr. Obaid last semester got pissed off at students because a lot of people forget how to write the equation of a line. So just a quick refresher. Y equals mx plus b. So in this case, okay, what's the y-intercept?
0.
0. So that's something. 0, and what's the slope?
1 over
If
pi.
it goes over the pi, or goes up 1 over pi, then it's 1 over pi. Okay. All right. So that's why we have t over pi right here. Then we have e to the negative j 2 pi over t. Okay. All right, so we can rewrite this. Okay, first of all, t is 2 pi, so that 2 pi and that 2 pi cancel out. Okay. I'm going to pull this pi out, so this is 1 over 2 pi squared. Now the integral from negative pi to pi, t e to the negative j n t. Yay, calculus. How do I solve this problem?
By parts.
Integration by parts, all right? Let's just do it as a refresher. I mean, typically, I forgot to bring it with me today, but there's a book called
Shom's
but Shom's.
Thumbs in
Yeah, and they're all online. You can buy these books that have integration identities. So if you don't want to actually do the integration by parts, you can look it up in one of those books. I use it all the time. Or I should say, as an undergrad, I use it all the time. I haven't really used it that much recently.
Can I push on, please?
Hmm?
So where you get 2 pi over t with the way you have the frequency? Well,
Okay.
yeah.
Because that's what omega is equal to 2 pi over t. Right? Which is the same as 2 pi f. Okay. Alright, so we want to solve this by integration by parts. What are we going to set u equal to? T. dv is, okay, so v in this case is going to be
1 over e to the j negative j and
sorry, I kind of crunched it.
e to the minus j.
Okay, and
You're taking the derivative.
Got canceled out because of the period.
no, you take the integral.
Period here is
You
2
go from
pi.
dv to
So
v.
2 pi divided by 2 pi is just 1.
And du
That
is
t
equal
is,
to
these two t's are the same.
dt. Okay. Because du dt is 1, so du is equal to. All right, so let's plug it in. Okay, so uv, so I have this is t, negative t over jn e to the minus j n t minus integral of v du. So this is negative 1 over jn e to the minus j dt. And we can solve that one now. Isn't too bad. Okay, so 1 over 2 pi squared integral, actually sorry, not integral, negative t over jn e to the minus j n t. Okay, minus and minus cancel out. Okay, so that's plus, I need to do this integral, which is what?
J squared n squared. So
Yeah.
the
So what
1
I need
over.
here, so if I take the integral of this,
Mhm.
this is just a constant. I can pull that out.
Mhm.
Okay. So that's plus 1 over Jn, and then the integral of this guy is also negative 1 over
Jn.
Jn, right? So this is times negative 1 over Jn. Minus J. We evaluate this whole thing from negative pi. Bring it up over here.
When we did parts, then we have to take another integral to b, because we're going from t to 1 to 0.
From t.
When we take the derivative of u, we got 1 and then we go to 0. I'm just trying to do like the parts thing, where you have your t derivative on one side and the integral on the other. You take your integral.
The tabulate method. Very by bugs. See, I don't remember the tabulate method. It's been, I think, like, I took that calc class in 2002. So it's been, yeah. So I just, yeah. So I do the good old fashioned UV minus integral of du, or U chunks. Because the less calculus I have to do, the better. All right, so let's pull this over here. So you can look that up and check it. But I know what I'm doing here is legit, as I will show you in MATLAB. Okay, so we have 1 over, this equals 1 over 2 pi squared, right? And let's pull out the jn's here. I'm going to pull out a jn squared. Okay. So if I do that, that is times negative t times jn plus e to minus j n t negative 5. Okay, that's just factoring.
Squared, yeah.
Jn squared.
It's,
I did this. I'll give you a word for that. Thank you. T minus. Okay, does that look good? Any other mistakes? All right, that looks good. All right, so jn squared is just j squared n squared, which is
negative
n
1,
squared.
negative n squared.
Okay, so this is going to be negative 1 over 2 pi squared n squared times, okay, oh, wait a minute.
I think that's
I think this is, yeah, okay. Yeah, you could factor out the e to the j and t as well. If you like, let's do it.
Don't you need to evaluate
Yeah, we're still going to evaluate everything from minus pi to pi. I'm just trying to rearrange it into simple terms if I can. So this is negative t times jn minus 1. I just like writing out all the math, just to make sure everyone's on the same page. So write down this little as much as you want. All right, so let's evaluate this. Negative 1 over 2 pi squared n squared. Okay. So e to the negative j n pi times negative pi j n minus 1 minus e to the positive j n pi times t times j n minus 1. Oh, actually, yeah, sorry. Okay. So how can we reduce this further now?
I think a negative one should be taken out of there, so they're gonna cancel each other out.
Okay. Alright, so we can cancel out. No, they will cancel out. Yeah. So okay, let's start here. Okay, what's this piece equal to? Okay. Let me put it this way. Alright, so okay, let's say n is 1, right? For n equals 1, that piece is gonna be e to the negative j pi. What's this piece gonna be equal to? E to the positive j pi. Okay. What does this actually equal? What does this actually equal? Alright. So those two things are actually equivalent. Okay. In this case, right? That's just because of the nature of this particular example. Alright, so those are equal. So I can just rewrite this as e to the positive j n pi. Okay.
Would that work for any n? Would they be equal for any n?
In this case, yes. Right? If n is 2, you have e to the negative j 2 pi, which is
1.
1. Right? And you will e to the negative j 2 pi. Okay. That's for this.
Okay.
That's for that x of t. Okay. For different x of t's, no idea. Yeah.
If the top one, right? So you're at j pi, negative j, imaginary you're down. That's negative 1, e to the positive j pi.
You have a unit circle, right? So e to the minus j pi
Is there.
is there.
Right.
Right? E to the positive j pi goes, yeah. E to the negative j 2 pi goes around twice. E to the positive j pi goes around twice. In the same place. Okay. All right. So those two pieces are equal. All right. So we can just factor that out. Okay. So we have e to the j n pi all over 2 pi squared n. Okay.
Wait, you really factored in that minus one of them? And then e to the j n pi minus e to the j.
This was a negative, but because they're equivalent, I just rewrote it as positive. Okay. I can factor this e term out. Is all I'm saying. Yeah. Okay. So this is now.
Can you have the negative e to the j?
No, but he's talking about this negative.
Positive 1 outside.
Yeah. Okay. So this is negative j pi n minus 1 minus j pi n minus 1. We're almost done. Okay. So this is negative j pi n minus j pi n. So that's minus 2j pi n. Negative 1 minus negative 1 goes cancel out. Okay. Alright, so this is now e to the negative e to the j pi n finally, the negatives cancel out. The 2 pi n cancels out. We're gonna have e to the j pi n all over. This is. This is why I never teach this class. Alright. So that's a lot of work. I write big. I'm sorry to make this sloppy. I hope you guys can. Okay. I'm going to. Let's put it up here. Alright. So after all that work, you could have just looked up Shams and gotten this equation in like 5 seconds, but I want you to practice. So this is. My MATLAB code is actually a little bit different than this. So another way of writing this is the same as negative e to the j pi n over j pi n. Okay? Because if I just multiply this by j over j, you get j squared over j, just negative 1 over j. Okay. So just for consistency, that's our answer. Okay, so for any harmonic, right, where n equals any integer, I should say positive. Okay. All right, so if I want to do it for the first harmonic, does this check out? Okay, e is negative j pi. Okay, so that's negative 1 times that negative. So that's 1 over j pi. Okay. Is that what we got over there?
Mm-hmm.
You guys said I was
That's from the J, right?
that's from the j. Yeah.
Mm-hmm.
Good. Thank you.
So wouldn't you say, like the other day you said not to leave it like that, leave it as polar, completely polar?
Yeah, it's better. It's better in general to convert it, but in this case, because we're going to plot it in MATLAB, it doesn't really matter. Okay.
When we convert though, for every even harmonic, it's going to switch the sign of the j.
Right.
So
Right.
express that.
I mean, you can like if you plotted it, it'll come out the same thing. It says the reason for this particular example that I left it like this is because you can see this is always going to alternate between plus or minus 1. Okay.
Oh yeah.
Right. So I'm going to show it to you right now. Okay. Why we left it like that? It's this projector actually.
I was just curious how you got from the negative.
Oh, it's because of 1 over j.
Awesome. Yeah.
Okay. So the ends all disappear because it's just 1 for the first harmonic. Right. So it's negative e to the j pi, which is negative 1. So it's 1 over pi. Right. Times e to the minus j pi. Okay. So good. Sanity check. That worked. Will this work?
That's opinion D. I wish they would have given us a fortuitous note or something. So we can get it upgraded later.
All right. So at this point, how many people are 100% comfortable plotting stuff in MATLAB? 80%. Okay. That's fine. So this is more good review of how to plot stuff in MATLAB. Is that better?
Where'd you get this?
I just recommend to you when you guys are using MATLAB, like everyone has a little bit of a different setup for MATLAB, but I think the 4 most important things to have visible at all times that will help you the most are obviously your editor window, your current directory, so you know what functions you have access to, your command window, if you want to just sort of fidget around with things, and your workspace. Okay, workspace is the #1 most important thing to have on here, because this is what shows you whether or not you're setting things up correctly in MATLAB. Like if you want a matrix, right, if it's supposed to be a 3x3 matrix, and you see in your workspace that it's a 2x3, you automatically know you did something wrong. And that is like the most helpful way to debug any of your code. Okay? All right, so going back to MATLAB, just sort of as a refresher, you guys always just stop me when you think I'm, if you want me to just move forward, just let me know. Okay, but I figure it's a good refresher. Clear. If I run this, first line will delete everything in my workspace. Okay. Sometimes, like I like putting this at the top of my scripts because every now and then MATLAB has trouble overwriting some of its data. So it's best to just clear it first rather than having to worry about overwriting it. I don't know. Maybe I'm just being superstitious. And CLF means clear figure. So if you have any figures open, it will get rid of those. And for the same reason I use clear figure. Sometimes they have trouble overwriting. MATLAB is one of those programs that takes a ton of memory, and sometimes computers don't like that.
What does CLC do?
CLC clears your command history.
Okay.
So like if I type CLC here, got rid of all my history.
Okay.
And I think I've mentioned this all to you before, but if you ever need help with the syntax, like let's say you're not comfortable with linspace, okay, but you know you should use it, if you type doc linspace, it'll give you the documentation for that function. As long as it's a built-in function. There's a lot of stuff you can find online from MATLAB that individual people have coded themselves. That documentation you'll have to look up separately. But the vast majority of things you'll need for this class are always built in. So when you do this, you can type help linspace too. I like doc because it actually gives you the syntax, and it also gives you, more importantly, examples of how to use it. So that's my spiel for why you should use doc. All right, so anyway, going back to our original problem. Okay, so for the first thing, I need to set up some sort of time vector if I want to show you x of t, right? So in this case, I'm just saying I want it to go between 0 and like 5 pi. Okay? It can be anything you want. It doesn't really matter. And then I'm saying I want 100,000 points. Okay. So if I actually look at this, if I ran this one line, I should have a vector that's 1 by 100,000. Okay, there's my first sanity check. Okay, so it is back 1 by 100,000. Okay, and that means that they're equally spaced. Okay, so that is 5 pi divided by 100,000. Whatever that gets you, that's the spacing between each point. Okay. This line I'm initializing x. As Dr. Bay told you about initializing things in MATLAB. Basically, every time you assign a new value to something, MATLAB has to reallocate memory for it. So with vectors or matrices, it's much easier if you tell MATLAB, like, I'm going to have a vector. I'm going to have a matrix. I don't know what's in it yet, but I know it's going to be this size, right? Because if you do that, it allocates that memory once, okay? And then you can fidget with each individual piece, no problem. All right, but if you say, I've got some variable x, okay, and I don't know how big it is, every time you change x, MATLAB has to reallocate memory for that variable. And when you do that, that makes your runtime like tens, if not hundreds, more than 100 times slower than what it would normally be. Okay, so always initialize your values for vectors and matrices. You don't need to do it for just like variables, whatever, but vectors and matrices, yes. Okay. So you can use linspace, you can use the function zeros or ones, whatever.
You multiply it by t, it's just
Because if I multiply it by t, then it'll give me a vector the same size as t. So if I ran this guy, it gives me x is now the same size as t. Okay. You can also, I could also write this as zeros, 1, like t. Okay, and it'll give you the same thing. Okay. Oops, that's actually x zeros and 2 1 zeros. Okay. You can use things like ones. Okay, or if you want something that's like all one die, you can, let's say you want everything to be 3, you can do 3 times ones, whatever you want. Okay. All right. So I initialize x, and then I'm saying, ultimately I'm going to want to look at maybe 100 harmonics. So now I'm just setting up a few things here. I'm going to say t is, my period is equal to 2 pi, this is from our original graph. Okay. And I'm going to say, I'm going to initialize a to be a bunch of zeros, and it's going to be a 1 by 100, 1 by 100 vector. A is your Fourier coefficient. Okay, that's what we solved for over there. Okay. So this is really a sub n. Alright? Alright, so now what I need to do, because my ultimate goal is I want to say, okay, like, is this right? Okay? How do I check if that thing is right? What do I do?
Like some won't get it wrong.
Right. I'm going to reconstruct my original signal. And if it comes out, you know, the exact same, then that means that that is correct. If it comes out different, then it means you did something wrong. Okay? So if I want to reconstruct it, what I need to do is I need to find every single value of A for every single harmonic that I'm looking at. Okay, so I'm going to use a for loop, and I'm going to go from 1 to the number of harmonics. I'm going to say that particular value of A is equal to, I left things in terms of the period, but you'll see there's always going to be a 2 pi that cancels out with that. Okay, so this is negative period of e to the positive j, negative period over j n squared pi squared times e to the negative j 2 pi squared n over t. Okay. This, I could rewrite this if you want, is exactly as that one. But for now, let's just run it and we'll see what we get, and then I can show that one to you. Okay? And I also want to say, what is the frequency at each of those harmonics? So I'm just going to record that as 2 pi over t times n. Right? That's omega n. All right? Now, if I want to rebuild it, I'm going to say, for this particular harmonic, right, this is our original function, 2 times the absolute value of A, okay, the magnitude of A, times cosine of omega t plus phi. Okay. So to get the this guy, that's what I'm plotting here. Okay. So where k is equal to 2 times the absolute value of A, okay, and phi, I have this handy MATLAB function called angle, which gets you the angle of it, or the phase of it, equal to angle A. Okay? And then to rebuild it, to rebuild the entire signal, I have to add all of these together, right? So what I'm going to do is I'm going to take my original function x, I'm going to add to that whatever piece I get for that given harmonic. Okay? And that's it. And then I'm going to plot a bunch of them. Okay? So S, this is my original signal, right? It is a phase shifted sawtooth wave. Do you agree? All right. What do you think about this plus pi? What's that from? Right. Because it's centered at 0 rather than being centered. Sorry, the 0 crossing at 0 rather than at plus or minus 1. Okay. So that's my phase shift. And then I'm going to plot this And just so we're not dealing with axes in like units of pi, I'm just sort of normalizing that out. So you'll see it'll be like 0, 1, 2, 3, 4. Okay. What's really important is that these two waves should overlap when I plot them. Okay? And then that's it. Okay? Alright, so let's run the first piece. Wow. Okay. So, it looks pretty good. Okay? It's not perfect. That's only because we used 100 harmonics, right? You technically have to use an infinite number of harmonics for this to be an exact match, which isn't really possible in MATLAB. So even if I went up to like 1 million, I'd get rid of some of the fringe effects here, but you still see a little bit. But yeah, it looks pretty good. Okay. What are some things to notice about this? Okay. So, like, what parts of the wave look good and what parts look bad?
Corners are very,
Yeah.
sharp corners and straight corners.
Yeah. Okay. And think about it, right? So for this piece here, this slope, this requires a bunch of low frequencies. Okay. Because you're just trying to make, like a line, right? So if I wanted to get that, I might, if I actually look at a cosine wave, right? Like this piece here almost resembles that line, right? It's a little bit curved. But if, maybe if I add to it a few other cosines, I get pretty close to that, right? Okay, so that's, you can tell on this part, okay, this is a low frequency component. Okay. Well, what about these lines here? How do these look? Up and down. Yeah. So you get something that's totally vertical, right? Like I do this kind of badly, but there's no real part of the cosine that's totally vertical, right? You get something that's like a total straight up and down line. I'm gonna have to add to it a ton of cosines, right? So it's gonna have much more of a high frequency component because you need many more cosines, ranging from low to high frequencies to get that piece. All right. So as I would go up in harmonics, you'd see that this fringe effect would kind of disappear because I'm adding to it higher frequency components. Okay. So just as like a sanity check, let's go back to our original code. All right. So if I change this to 10, what's going to happen? It's going to look a lot worse. And it does. And you can see that, like, this piece is now, a little wiggly, but the major wiggles are still at those corners, which makes sense when you think about it too, because this is like a discontinuity, right? This is very hard, a hard thing to recreate. Whether or not it's a square wave or a sawtooth or a triangle wave, any discontinuity is going to require a much higher frequency component than other parts of the graph. All right, and then if I up this to, I did 100 before. Let's see if MATLAB barfs if I do 10,000. It might. Give it a minute.
Need to send them away.
Well,
There we go.
wow.
Okay, it's getting much better, right?
Jesus.
There's not as many oscillations here. There's still some issues, obviously.
Just zoom in, you can see.
Yeah.
It's gonna.
Okay. So you can see it's getting a much sharper pointer, right? So good. That's doing exactly what we thought it would do. All right. So the last thing I want to show you. So we have now verified that we have actually calculated the correct Fourier coefficient. We've reconstructed our wave. We have a very good approximation. Everything checks out. Okay, so the last thing I want to do is I just want to show you magnitude and phase plots. All right, so if you wanted to look at the actual components, like which frequencies have how much energy. Okay. We need to look at our magnitude and our phase plots, right? Because that is a complex number. Okay. So I'm going to say the magnitude is the absolute value of every A, and the phase is the angle A. Okay. And then typically what I like to use is a stem plot instead of the actual plot function. Stem just means for each index, it'll give you like a straight line showing the value at that point. Okay. And just as a refresher, if you're not familiar with subplot means it's going to create a figure that has one row, two columns, and this means it's the first piece of that. Okay, so this will be the graph on the left, and then this one will be, first row, second column, second graph. Okay, so I'll plot them side by side. All right, and then you can label the x-axis, label the y-axis, title it, and then I'm just saying I want my limits to be between 0 and 15 on the x-axis. Okay. All right, so here we go. All right, so you can see, let's look at the graph on the left first. This is the magnitude plot. Okay, so most of the energy of this wave is at lower frequencies, right? Like you can tell it's got this huge point right here. If I wanted to go out much further, you'd see this kind of is like an exponential decay, right? So there's still a fair amount of energy, at higher harmonics, but compared to the lower harmonics, it's much less. Right? Yep.
Does the limit approach 0?
Yeah. If you went out to infinite harmonics, right, like the infinite harmonic would be 0 energy. Okay, and then we're going to look at our phase, all right? So,
could you also say that the reason we have a lot of energy for the magnitude plot could be because the original sawtooth has a 1 to 1 negative.
well, it's got a lot of energy at low frequencies because of this portion of the graph. Okay? Like most of the graph is a continuous function. Parts of the graph are discontinuities. So that's why there are high frequency components. Okay? What would it look like if I wanted to look at the magnitude and phase plot of a cosine? What does that look like?
Just one frequency at that
Right.
frequency.
Yeah, like if you're looking at positive and negative frequencies, it's a goalpost. If you're looking at only positive, it's one post.
One post.
Right? There's only energy at one frequency, right? Like cosine of omega t has energy at omega. Right? That's it. No other frequencies. But the sawtooth has it at an infinite number of harmonics, infinite number of frequencies. Okay? So let's just try to make sense of this real quick. Then I'll let you guys go. All right, so look at the magnitude plot. Is that in line with our Fourier coefficient? Should the value of A, the magnitude of A, decrease at higher frequencies? Yeah, because there's an n in the denominator, right?
Mm-hmm.
So the magnitude should always be decreasing. What about the phase? Does that make sense? Right. Right. So we know, okay, so this J is actually part of the phase 2, if we convert that, right? But we know no matter what happens, there's this component, which always means every other frequency, every other harmonic, this is going to flip between positive and negative, right? And this piece indicates there's going to be pi over 2, right? So that makes sense. We're at roughly plus or minus pi over 2. Okay. So that makes sense? We've sandy checked ourselves. Things look good. I think that's all I got for you guys today. So does anyone have any questions?
Text your code to the plot commands.
Yeah.
The one before that. Yeah, down to minus.
Yeah. So, like I said, I divided everything by pi. Because if you think back to our original graph, it was from negative pi to positive pi. So what I wanted to show you is that I didn't want, I thought it would be a little bit more clean cut if we just went from, -1 to +1. Right. So this is 1 is pi. This is 2 pi, 3 pi, 4 pi, 5 pi. Okay. So the units are seconds. Any other questions? Yeah, I can post it myself. I'll put that up for you guys. Okay. So things to remember, because you will be doing this for homework projects. You'll be doing like Fourier transform or Fourier series things for your computer projects. Remember, if you're trying to reconstruct a wave, you have to find that particular component. Okay, this is really important. That you find the component at that frequency, and then you add it to the overall reconstructed wave. Right? Because if you left out this line here, you wouldn't reconstruct your wave, because you just get that X harmonic is, like this value for this frequency, right? Like,
Yeah, every part you get a bunch of cosines on top.
Right. Right. They wouldn't even be on top of you, or yeah, they would. Yeah. You get a bunch of separate cosines.
Yeah.
All right. This piece is actually reconstructing it. So always remember that. Okay. Any questions? All right, you guys good? Have a good day. I'll see you in the recitation today. Otherwise,
What kind of hardware do you have on that machine?
I don't know.
If you're curious, go down to start, then right-click my computer,
oh, I have quizzes. Come get quizzes.
then hit properties.
It's a virtual machine, though.
No,
It's
this
running
is.
on
I'm going to warn you. I took
It's real.
points
It's
off
under.
if
It's in my
your,
closet back
It's a
home.
Pentium
signs
4
of the phase
2.8
is correct.
gigahertz.
Because
knew
I
it was
have recorded
good.
that same thing on Fire before.
You could probably get it up to 2 gigs of RAM.
Thank you,
Pete,
Craigslist.
where's Pete?
How much? Oh yeah, I could.
Joe. Not Joe. Joe.
I've got a computer from about the same time period.
Oh yeah, yeah. I like it so far. It's worked out great. Oh, thanks.
Brian?
Yeah. Brian or Brian?
Brian, right there. Thank you.
Working. I think Dave might have been working on the Lunabot server
Oh yeah.
right now, so maybe he was slowing it down.
No, I actually did something incredibly stupid, which is definitely slowing it down right now. Actually.